Hi everyone, my name is Prerna and I am from Team 12. Our team worked on the chest X-ray disease diagnosis project. The agenda of this presentation is to provide a quick demo of our project, including the high-level approach, implementation details, and results. Chest X-rays are the most common form of medical imaging used for detecting pneumonia and other lung-related diseases. But diagnosis from these images requires careful observation by expert radiologists and often leads to conflicting results. Researchers have been trying to solve this problem by developing computer-aided solutions using various chest X-ray datasets. Our project also applies deep learning methodologies from the area of big data science to the chest X-ray 14 dataset. This is publicly available by NIH, and it contains over 100,000 X-ray images with text-mined 15 labels, out of which 14 are common thoracic diseases and one is a no-finding label. Initial summary of the data shows its imbalance in terms of labels, as 35% of the images have no finding label. There are many research works done in the field of chest X-ray disease diagnosis. Some include using pre-trained CNN models for multi-label classification, like the ones presented by Wang et al., and the ChexNet model developed by Rajpurkar et al. A very unique approach presented by Yuxing et al. Converts this multi-label classification problem into binary classifier. We include this as one of the approaches in our project, and Sagar will discuss more about that in detail.
Thank you, Prerna. So we have taken two approaches to solve the chest X-ray disease diagnosis problem. One is the multi-level classification using deep convolutional neural networks from pre-trained networks by directly predicting the 15 unique labels. And second is the one-class classification problem using adversarial learning by building a deep convolutional GAN to differentiate between normal and abnormal chest X-ray images. Moving on to next slide. We have mainly used Python Jupyter notebooks for our implementation and popular Python packages like Pandas, NumPy, Matplotlib for data processing and results. For our implementation of convolutional neural networks, we are using Keras with TensorFlow backend, and thanks to Google Colab Pro environment, we were able to get GPU access as well. Moving on to next slide. For our multi-class implementation approach, we have basically used transfer learning using DenseNet and ResNet pre-trained models. The authors of the DenseNet paper show that by connecting every layer of neural network with every other layer, they are able to better use a feature in deeper layers of the network, and DenseNet can achieve state-of-the-art results by less parameters and less computation operations compared to ResNet. For our transfer learning approach, we also add a couple of dropout layers and global average pooling layer to reduce overfitting. Moving on to next slide. For the one-class DC-GAN approach, we have built a 5-layer UNet autoencoder generator model and a 5-layer CNN discriminator model. The goal of the encoder is to take a normal chest X-ray image and create a latent representation of that image. The goal of the decoder is to take that latent representation and try to reconstruct the original input image. Now, the goal of the discriminator is to take as input the original input image and the reconstructed image from the generator and try to classify which one is real and which one is fake. After the generator and the discriminator have been trained for a few hundred epochs, we move on to the inferencing. The anomaly score, the final anomaly score, is created as a combination of generator reconstruction loss score and the discriminator score. Since the network has only been trained on normal chest X-ray images, the expectation is that the anomaly score will be lower for normal chest X-ray, whereas it will be higher for abnormal chest X-ray, which might contain some diseases. Now, Jesse will go through all the results.
Okay, thank you. For ResNet, the model implementation is already explained to the previous slide. In our model, the AUC scores of effusion and infiltration are actually comparable to the results in the Wang paper, and for pneumonia, it outperformed the original paper. And the DenseNet, the average AUC results are actually in line with the ChexNet paper that achieves a better average AUC value than the ResNet architecture. So in our training, DenseNet versus the ResNet average AUC is 0.79 versus 0.63. In addition, we experimented different hyperparameters in the DenseNet to highlight batch size of 32 actually perform better than 16. And also the deeper the network, the better the results. We followed one of the suggestions, the previous slide. Yeah, we followed one of the suggestions in the paper to use a weighted loss function to solve the imbalance in data. But more work is needed to achieve a better AU-PRC score to differentiate false negatives. And on to DC GAN. The training on the generator and discriminator was conducted on a portion of the images with the no finding label. Test set was also on a portion of the no finding images versus the abnormal X-rays with pathological labels. On the right, you can see a set of X-ray images generated from our GAN. And since the image quality is not as good, the final classification results between the normal and the abnormal X-rays was around 0.54 AUC. It's because the discriminator can easily distinguish between the two, real and fake images. And conclusions. We used deep learning approaches to develop multi-label CNN classifiers and DC GAN as a binary classifier. We also learned about the hyperparameter tuning and transfer learning imbalance data techniques throughout the process. Just met were limitations in GPU and the sensitivity of DC GAN with respect to hyperparameters. Future work include more work in improving the AU-PRC to handle class imbalance and to improve the DC GAN by modifying the UNet and adding the second encoder as in the paper. Finally, here's a list of the references, and that's the end of our presentation. Thank you for your time.